Yeah, that's fine. If you let me move them up here. That way they'll be right there. If you don't mind working on top of this notebook, do you? Good morning, everybody. We're going to try to get the program started here in about 5 minutes. So if you can finish up your breakfast and start moving into this room and filling up all the tables toward the front, we'd greatly appreciate it. Good morning. If you would, please, we're trying to get started here, so if everyone out there in the dining area can start moving up toward the speaking stage, we'd appreciate it. Good morning, everyone. We're going to get started here. I'd like to invite Don Ward up onto the stage. He has a few comments.
Good morning, everyone. Welcome to day 3. The next keynote speaker is David Ruggiero, chair of Globe. A little bit of background first about that. CIB is a member of a liaison committee of major civil engineering associations, which first met in 1958. The other 5 associations are the International Association for Bridge and Structural Engineering. Bear with me on this. It is, I think, interesting. The second one is the European Convention for Constructional Steelwork. Third one is the International Federation for Structural Concrete. The fourth one is RILEM, Réunion Internationale des Laboratoires et Experts des Matériaux. You can see why we changed the name of CIB from the French version. And the International Association for Shell and Spatial Structures, IASS. And that committee, as I said, first met since 1958, so it's almost as old as CIB. And there is value in these associations collaborating over the years. And in particular, actually, several of our commissions have been joint groups with those associations. So, for example, still to this day, W56 on sandwich panels is a joint one with ECCS, and W83 on roofing materials is joint with RILEM. So I think that's useful to understand where these connections come from. The liaison committee formed the JCSS, Joint Committee for Structural Safety, in 1971. And that in its field of structural-related risk and reliability, is a global leader in its field and very significant in producing codes of practice and so on. And through the JCSS, an initiative developed in 2019, which became known as GLOBE. And I'm not going to steal David's thunder by telling you anything about that. Suffice it to say that it has its own board, and the CIB's representative on it is the coordinator of W116, which is Smart and Sustainable Built Environments Working Commission. And the coordinator of that is the co-coordinator now is Jeremy Gibbard. The other one is Jan Hugo's here. But Jeremy Gibbard is on the board of GLOBE. But the new chair of GLOBE, as of, late last year, actually. Yeah, yes, I was just thinking time has already flown, is David Ruggiero. And I'm pleased to ask Jim to read his biography, and then we'll welcome David to the stage. Thank you.
Thanks, Don. David Ruggiero is a tenure-track assistant professor of structural design and engineering at EPFL Switzerland, where he leads the Construct Laboratory. He received his PhD from the University of Toronto in Canada and previously practiced as a structural engineer at RJC Toronto, where he was a designer of high-rise buildings and other complex structures. Ruggiero aims to advance sustainable design through improved understanding of structural behavior. He serves as chair of the Joint Committee on the GLOBE Consensus, an international initiative to promote sustainability in the construction sector. Please welcome David Ruggiero to the stage.
Okay, thank you very much for the introduction, Jim and Don, and for the invitation to be here. It's a real honor to be speaking to you all today. As Jim said, my name is David Ruggiero, and I'm a professor at EPFL, the École Polytechnique Fédérale de Lausanne in Switzerland. And it's a beautiful place on the Lake Geneva, so if you have a chance to visit, you definitely should. I'm originally from Toronto, Canada. And I worked there as a practicing engineer, mostly designing tall buildings at RJC Engineers. And as has been said, I'm here in my capacity today as chair of the Joint Committee on the GLOBE Consensus, the Global Consensus for Sustainability in the Built Environment. So my talk today will be a mix of research and professional and association experiences with a bit of a structural engineering perspective on how we can really work towards making truly sustainable buildings and sustainable construction. I mentioned GLOBE. For those who aren't aware, GLOBE is a cross-institutional initiative for advancing sustainability in the built environment that comes out of this foundational document that Don mentioned, which you can access on our website in several languages. It sets out a vision for sustainable construction within our planetary limits and acknowledges that we need a global effort from all stakeholders to be able to reach our sustainability goals and mitigate the consequences of climate change. GLOBE was created by this joint committee of 6 leading international associations, and I think CIB brings maybe the broadest base of expertise of these 6 associations. But we also have the expertise in steel construction, concrete construction, structural materials in general, conceptual design and shell structures, and structural engineering and infrastructure. So this is the DNA of GLOBE. This is what I think sets us apart from other similar initiatives, is that we have this wealth of scientific and engineering expertise for a more data-oriented approach to this problem. And a big part of it is being able to form bridges between the different silos, the different focus areas, with an understanding that we need this cross-disciplinary approach to sustainable construction. Now, I titled this talk Engineering Within the Limits, and that's what we're here really to talk about. This is illustrated well in this concept of donut economics put forward by the economist Kate Raworth, which I think is a great picture. We have two limits that we need to navigate. The lower limit is the minimum amount of resources that we need to expend to ensure a basic social foundation, housing, water, energy, food. So well-being for the people, the inhabitants of Earth. Whereas the upper limit represents essentially the carrying capacity of the planet and the maximum resources that we can use without harming the environment in an irreparable way. It's called the ecological ceiling here. And the trick, the economic challenge, is staying within these two limits. And in fact, sometimes defining the limits and determining just how much room there is to navigate, if any, between the two limits. And from a construction point of view, we might identify the need for sufficient housing as one of the key pressures, for sure. I mean, we know that the demand for housing and for new building in general is not letting up. The Earth's population is still growing. Right now, China is still building something like 1,500 square kilometers of additional new floor space every year, not counting replacement of structures. But even as demand in China is forecasted to slow after 2030, we just expect to see the demand shift south to Africa and India. So this represents a real challenge because at the same time as we're trying to decarbonize construction, we realize that we still have entire cities that don't exist today that need to be created, or housing 80 million people in Dar es Salaam by the end of the century. Well, it's also an opportunity in the sense that we can learn from the mistakes that we've made over the last 100 years, say, and now we have the chance to build better the next time around. But it really is an immense problem. Put another way, we need to build another New York City every month for the next 40 years. And we know that buildings are a huge source of global emissions, on the order of 40%. And today, most of those emissions are operational, but as we see a shift towards green energy sources, as the grid becomes cleaner, we'll have a more and more important piece of that pie in embodied emissions, that is, the production of construction materials themselves. And within this chunk of embodied carbon, most of those emissions are due to the structural elements in our buildings, not the finishes or furnishings, but the concrete and steel and timber. And it varies from case to case, from building to building, but you can figure that structural embodied carbon accounts for maybe 60 to 80% of the embodied emissions in our typical buildings. So I think the role of structural design is critical. We want to limit the carbon impact of our construction, but we generally need to limit the amount of structural material that we use. And how can we do this to truly create sustainable buildings? Well, we've heard a lot about the Sustainable Development Goals, and in my talk I'll mostly be alluding to Goal 11, Sustainable Cities and Communities. But I want to pick on the UN, or the UN website team here a little bit, because this picture coming straight from the website has this background for SDG 11, the picture of the Bosco Verticale in Milan, which is a beautiful building, which is notable for the greenery and all these trees on the balconies. So there's this idea here that maybe this is what a sustainable building should look like, and it's certainly green on the outside. And we see versions of this green building popping up all over the place. There's a similar project also by the same architect, Stefano Boeri, for the city where I live, Lausanne. But here's the thing. Soil and trees and all this greenery is heavy. And it's particularly heavy if you stick it on the end of a cantilevered balcony. And in fact, a local engineer, Julien Paté, made some estimates and looked at the structural requirements of housing all of this greenery and found that, in fact, well, you have a 66% increase in greenhouse gas emissions in the structure because of the additional demands of carrying those trees. And in fact, it would take 20,000 trees to offset the embodied carbon of the structure, not the 80 that they're planting on the building. So So I think this is illustrative. I think we shouldn't fall into the maybe emotional trap of saying that we want green buildings, therefore we need to cover them in plants. And now, there might be psychological benefits, societal benefits to having this kind of architecture as well. I'm not saying that there's not, but it comes at a cost. So you have to know that these are complex systems, and there's always more complexity to it than our first superficial gut reaction. But what can we actually do to improve the sustainability of our built environment then? Well, the bad news is that there's certainly no silver bullet. I don't really believe anyone who thinks they have a magic wand that they can just wave and in one fell swoop solve everything. It's going to take work, and it's going to be the accumulation of a lot of incremental improvements. 5%, 10% in every place that we can squeeze it out. And then it starts to make a real impact. I think we need to take a holistic view and target improvements across different scales. So for example, the material scale, the structural scale, the urban scale. And as a structural engineer, I live mostly in that middle box, and I'll try to show you some things that you might not have seen before there today. But within Globe, we have the expertise that crosses all of these scales. So let's see what we can do. Well, we know that we use a ridiculous amount of construction materials. This graphic underlines just how much. We're not using it just for kicks. This is all towards that goal of meeting the societal demand, the needs, the social foundation of providing housing and infrastructure for humanity. But you can also appreciate that it would be very difficult to replace these conventional materials by something else. There's unlikely to be a new miracle material that we don't know about yet that's going to be able to substitute all of this concrete, for example. People sometimes get very heated and very dogmatic about construction materials and will argue that there's an obvious best material, but I don't think that's really the case. When we talk about structural materials, at least, in fact, we tend to find that they're all in the same ballpark when you account for embodied carbon and strength, if you look at the specific strength. There are studies like this one that show that different flooring systems have different optimal typologies depending on context. So for example, the span length. And there's no single solution that's a one-size-fits-all. It depends heavily on location, transportation, local value chains, etc. Mass timber is seeing a great renewal, which is nice. I like wood as a material, and it makes for very warm, pleasant buildings. But as noted by Arup here, it's probably not going to be possible to replace all of our construction with timber. For one thing, there's not enough global capacity for sustainable forestry. There's been some opposition, for example, by a group of hundreds of forestry scientists who addressed a letter to US Congress stating that they don't support more logging for construction. So it's clearly a complex issue, and me personally, I prefer to see the potential of all of those gigatons of concrete that we're using, where if we can make a 30 or 40% improvement in our concrete, that is going to scale up massively. So one technology that I'm excited about is limestone calcined clay cement, or LC3, which allows replacement of about half of the clinker, the really carbon-intensive part in our cement. And in our lab, we're doing verification studies to show that concrete made with LC3 performs just as well as ordinary concrete, and in fact, we have some exciting results that show that in certain cases, it's even better, for example, for long-term behavior. So this is just scratching the surface, but to summarize, I don't think that there's any magic material that's going to solve all our problems. Rather, we should be focusing on using the right materials for the right jobs and taking advantage of existing networks and value chains to scale up our improvements. Now, at the structural scale, this is my personal focus and interest. There's been a shift in the last couple of decades that maybe you've noticed in the types of structures that we're designing, that we're being asked to design. CAD, BIM, more powerful desktop structural analysis are enabling us to build more and more complex structures. 50 years ago, our buildings were based on regular grids, uniform spans, simple systems. Today, on the other hand, structures are exceedingly complicated with these skewed elements, very thick walls, walk-in columns, transfer slabs, and generally things that don't line up one on top of the other. It's kind of Jenga towers. And in the extreme, we see something like this, where I think even a layperson can look at this and see the complexity. And basically, if you have a building that looks like it wants to fall down, it probably does want to fall down. And as the engineer, you're going to have to do a lot of work to make sure that it doesn't. You have to put in a lot of material, a lot of concrete and steel and pre-stressing. And obviously, that all has an embodied carbon toll. So you're fighting gravity to make these things stand up. Now, it's a bit anecdotal, but I'm trying to find ways to study this in my lab systematically. And we have had students do design projects where some of them introduce these kinds of irregularity into the structure, and we compare the overall average embodied carbon and see that, yeah, in fact, the more irregular the structure is, with bigger cantilevers, bigger spans, hanging parts, then the larger its carbon footprint, which makes sense, I think. And I also did a study with some colleagues in Australia on this building, the Melbourne School of Design, which has a large cantilever. We did a thought experiment of removing the cantilever and found that you could save a significant amount of embodied carbon associated with that floor area if you just added these columns. So you're definitely paying a carbon premium for having a cantilever. Here's a beautiful cantilevered structure, the America's Cup building by Sir David Chipperfield, the architect. But in fact, even he's come around. He says, I used to love cantilevers. You'd go past a building and see a beautiful cantilever. Now I just think that's expensive in energy. You have to adjust your perception of beauty as well. But I don't want to give the impression that this is just a problem of these showcase landmark structures. Actually, it's not the case. There's a much more, I think, insidious problem that's creeping in to even our very typical structures. And I'll use as an example a project that I worked on in Toronto, for better or for worse. It's a pretty boxy looking condominium tower, and it's fairly regular with repeated floors in the tower, but the podium is a bit of a dog's breakfast, the technical term. It's got resident parking, it's got municipal parking above grade, it's got retail, amenity, lobby, sky lobby, mechanical space, I think a bowling alley, and all of these have competing spatial demands, and they want to have different structural grids, and as a result, there's, among other things, a very thick transfer slab, or transition slab to accommodate the changing geometry, and if you look at the floor plans going from bottom to top and overlay them on each other, you can see that it's really quite a mess. You have the regular parking grid, but then you have these ramps, and then you start to get into these new stair cores, and then in fact the elevators and the main walls for the tower that fall right over top of the parking drive aisle below, for example. And here's that main transfer slab in 3D. So you can see the structural grid below and the structural grid above, and they don't match. So basically, what we had to do was insert a 3-meter thick or 10-foot thick solid concrete transfer slab. That's pretty much an entire story of reinforced concrete. There's as much concrete in that one slab as in 15 floors of typical slabs above it. And that was the only way to make it work that adhered to the codes and essentially to the architectural and programmatic constraints. And the simpler solution, of course, would have been to say, well, just line up the structure from top to bottom. But we were too far gone by that point. There was too many demands on the client side, the number of units that they needed to create, and the municipal requirements for the parking below. So I think this is unfortunately pretty common, that when you're stuck with something like this, the structural engineering solution nowadays is just to brute force it and put in a massive slab. And we see these in a lot of buildings. Here's some similar pictures of different projects where you're walking around the forest of rebars taller than a person. And we've also tried to study this quantitatively in my lab, so just how bad is it to have a transfer level in your structure? And for the case of transfer beams, as shown here, we've seen that you're adding 20, 30, 40% to the embodied carbon of the gravity structure just by introducing one transfer level. And it's not just one building. This is endemic. It's every building I've worked on in my career. You see it more and more, these kinds of structural gymnastics with cantilevers or transfer slabs or cantilevered transfer slabs. And every time you have that, you're multiplying the amount of material you need to make the design work. So in an analysis of one company's projects in the city of Vancouver, this engineering firm found that transfer structure accounted for 17% of all overall embodied carbon in their buildings. And so I've snapped pictures just walking around Toronto, and you can see these things on display. Here, for example, will be the tallest building in Canada, all supported on one big transfer beam or transfer blob, and also this 2-meter thick slab. Just pretty typical buildings, nothing out of the ordinary. This is a 15-foot deep transfer level. And I'll pause here for a second on my new least favorite structure. Look at those columns. Not a single one lines up from top to bottom. So every floor is a transfer floor. Every slab needs to be 20 or 30% thicker to make this work. So it all adds up very quickly. So to summarize, as a structural engineer, I'm convinced that we could easily shave 20% in carbon from most of our buildings. But it requires a coordinated optimization with the entire team, first of all, the architects, owners, contractors, mechanical, electrical. I didn't even start talking about electrical conduit in slabs, which is another pet peeve, but anyways. We can still design interesting buildings, but we should prioritize having rational and simple load paths. So direct flow of forces, that's always going to be optimal in terms of material, in terms of carbon, usually in terms of cost as well. And there are also some things we should do regarding codes and policy, because we live in this kind of implicit world of minimum standards and over-design. Everything is ultimately over-designed, so we need to think about upper limits as well. Finally, zooming out to the urban scale, here we have some really interesting interplay between complex systems, and maybe this is where some of you come in. Well, we know that the world is becoming more urban, more vertical, in fact. And this graph shows the number of skyscrapers in existence taller than about 40 or 50 stories. This is cumulative. And it's exponential. It's literally exponential. The doubling time is about 8 years. Yesterday we saw Moore's law for transistors, so I'll say this is Moore's law for skyscrapers, or maybe Ruggiero's law for skyscrapers. So today there's more than 5,000 of these skyscrapers in the world, and when I was born it was maybe less than 500, and who knows in another 30 years what it'll be. This is new territory. This is, we don't know what our cities are going to look like in 50 or 100 years. In particular, when these buildings start to get old. And we also have to ask ourselves, what do we want our cities to look like? What is the ideal urban form that's going to allow us to live between this social foundation and ecological ceiling? My hometown of Toronto is a good example of that kind of vertical growth. 50 years ago, the first skyscrapers were built, and since then, it's been essentially nonstop. That's the same view. Today, Toronto is the 4th largest city in North America after Mexico City, New York, and LA, and it continues to grow. I think it's had the most tower cranes on the continent for the last decade. And as fulfilling professionally as it's been to personally be part of making that skyline, I have to ask myself if we're doing the right thing, if this is the right built form. Now that I live in Europe, I can't help but compare, for example, the new neighborhoods in Toronto with this typology of pencil towers, with the kind of uniform density of a city like Paris or London or Barcelona, that achieves a similar density of housing overall, but has a completely different urban environment. You can see on the left even the amount of space that's devoted to roads. This is right in the middle of downtown Toronto, but it's still a very car-centric model. And the other thing is that the tapestry of a city like Paris seems to me to be inherently better for allowing adaptability and regeneration, and reuse, reinvention of the space, whereas these mono-block towers are kind of all or nothing affair, and it's hard to imagine how these could be reinvented in 50 or 100 or 200 years. And others have looked at this question as well about what's an ideal density and an ideal urban form and what kind of buildings we should be building, but it's a complicated, multidisciplinary question. I'll say just from a purely structural point of view, we know that as you go taller, you end up using more material, mostly because you're fighting the wind, so you have higher embodied carbon per square foot. But going taller also allows you to have other economies of scale with transportation, for example. So density where you have the proper infrastructure in place can be quite efficient, but how tall is too tall? And this topic has entered the public consciousness over the past few years, and you might have seen this tower in New York, 432 Park Avenue, in the news again last week, I think, as the tenants are suing the owners over cracks in the building's walls. And New York has seen the construction of these ridiculously slender pencil towers, and people are starting to question the trend. For one thing, it seems like a lot of these super slender buildings actually have performance problems with swaying in the wind, and people just don't like to live in them. But I think on the other side, we have to question if these are really just vanity projects for the ultra-rich, where you have, the sky getting blocked out for the sake of a couple of billionaires. And you have maybe a 100-story building with 100 units in it, and more than half of them might be empty at any time. So is this really an efficient use of the planet's limited resources and carbon budget? There's one extreme here on the left, that's the Steinway Tower with 2-meter thick walls to reach these outrageous heights. And so you have all of that embodied carbon for a few people, and it sometimes makes me think that as a baseline, we shouldn't be talking about expressing greenhouse gas per square foot, but perhaps greenhouse gas per capita as a baseline. But on the other hand, on the right, we have a floor plan of a low-rent building in Toronto, and you can see why this is kind of suboptimal for a different reason. Well, these apartments have something like 400 square feet, and they're mostly corridor, so you're just squeezing people in, and have to ask yourself how adaptable this is in the long term, or if they're just going to knock this down in a few years. And we definitely don't want to incentivize cramming people into these kind of tenements just to minimize a metric of carbon per capita. So we need to provide a reasonable quality and quantity of space, that's our social foundation on the right, without exceeding the ecological ceiling on the left. And there's another aspect of this that I don't hear frequently discussed, even when talking with owners about these massive construction projects, and that's what's going to happen to all of these skyscrapers in 50 or 100 years, when they're old, at the end of their service life. I think we need to take a longer outlook. We're talking about massive amounts of material here to build these things, so it's not something that should be rushed into. There's a complex interplay between structure and architecture here, because the structural bones of a building, if it's well protected, should be able to last essentially forever, but other parts of the building will start to fail. The envelope, the mechanical systems, things will get out of date, obsolete, even fashions change. And unfortunately, in today's development environment, it's often more economically appealing for the owner to just tear the building down and build something new rather than to maintain it. I'm being a bit tongue-in-cheek here. I'm not saying that every building needs to last for millennia, but for some economic reasons, we sometimes have perfectly good structures like the one at Wright that are being demolished when they're still kids, basically, not even middle-aged. And it's also starting with skyscrapers. 270 Park Avenue in New York was SOM, 200-meter tall, internationally acclaimed building when it was built, and it was only 58 years old when it was demolished. And even more recently, the AXA Tower in Singapore, 230 meters tall, the tallest building ever demolished, was only 37 years old, so younger than me. And this one had a heavy concrete core. Just look at the machinery that has to be hoisted up there to chip away at it from the top down. I think it took longer to demolish it than it did to build it in the first place. It's just such a waste of resources and energy. So when we talk about sustainability in a holistic sense, I think this is the bottom line, that we need a plan. We need to set a goal for what we want our cities to look like in 50 or 100 or 200 years. We need to look at the life cycle, and we shouldn't just jump in and build because we can. And then if we say that, well, we don't want to demolish buildings, or demolition becomes economically unfeasible in the future, then what happens? Well, this isn't a look into the future. This is the present. This is the Tower of David in Caracas, Venezuela. In this instance, the building was never finished as originally designed, so it's a bit different, but it essentially turned into a vertical slum. And on the one hand, it still provides some form of shelter, which is what buildings are here for in the first place. But on the other hand, no water, no power, no elevators. So I think we can agree that this isn't what we should be aiming for in terms of quality of life, in terms of safety, reliability, and in terms of reuse. This doesn't meet our bare minimal social responsibility. So we need to be very selective about what we're going to build. If possible, we shouldn't build at all. The 3 R's, reduce, reuse, recycle, but most important is probably refuse. So challenge the brief. Don't build just for the sake of building. We should use existing structures when possible, considering that their carbon has already been expended to create that skeleton. And if we do need to build new buildings in places where we do, then we should think about their entire life cycle and how we'll deal with them as they age and ultimately prevent their needless demolition one day. And these questions about ideal density and ideal shape of our future cities are complicated, but I think increasingly important in the context of the population boom that's coming in some parts of the world. I'll wrap up by putting on my scientist hat and saying that if we want to attack this multi-scale, this multivariate optimization problem and find real solutions, then we need to start with better data. And we need to be able to see what the hotspots are to establish baselines and benchmarks for where we stand today and where we want to go in the future and how we're going to get there. So to this end, I'll introduce the Global Building Data Initiative, GBDI, which is an initiative that was launched under the GLOBE umbrella in an effort to harmonize whole life carbon reporting and create a global database of building information. So the GBDI team has developed an open data format, OpenBDF, that you can read about, as well as this web platform that you see here, where organizations can contribute their own data. It's online, it's free to use, so you can access it and try it out. And we're happy to collect feedback as well, or to arrange meetings with any groups that might have their own databases already that they would like to roll in and contribute. And just another pitch, we'll have a Globe sustainability seminar and Globe meeting at the IBRACON Concrete Congress in Curitiba, Brazil in October. And in general, if you're interested in this or in being a part of Globe as already a member of CIB, if you'd like to contribute to Globe in any way, please feel free to use this link here to register, and you'll be added to our membership and to our mailing list. So I'll close with one last quote. It comes from an oath that graduating civil engineering students at my alma mater, University of Toronto, would make based on Jacques Cousteau's Bill of Rights for Future Generations. It says that all appropriate measures shall be taken to ensure that the rights of future generations are protected and not sacrificed for the expedience and convenience of the present generation. The days of being able to build whatever we want without consideration of the impact are over. It's our responsibility now to work together to keep within the limits, to guarantee not only the quality of life for our generation, the current social foundation, but also to safeguard the environment, to respect that ecological ceiling, so that our descendants will be able to achieve the same social foundation. So it all comes full circle, really. Achieving net zero construction or near zero construction is not going to be easy, but I think we need to consider all of the efficiencies and savings that we can achieve at all levels, at all scales, and work towards making a building stock that is truly sustainable and not just green on the outside. Thanks very much for your attention. I'm happy to answer any questions.
We have time for a few questions, if anyone has any.
I can belt out the first one. I've been told I don't need a mic. So, David, first of all, really enjoyed your presentation. Very thought-provoking, kind of an interesting look at the issue of carbon and where we're seeing some excessive use on that. Thank you. So my question is, I was thinking about this, and I was thinking about the design team early on in these processes, and a lot of these buildings are probably built with a design build or CM at risk or other more collaborative type of building approach where you've got the whole team right there. Who do you see is championing this idea of looking at the design? So, you're not using these excessive transfer slabs and you're getting better continuity of the structure, or who should be championing that? Who takes the lead in this? Because, the architect is looking at the aesthetic side, the constructors there to, looking at the building side. I'm just curious I realize it's probably ultimately everybody, but is there somebody that really needs to step up here?
Yeah, great question. I think that the structural engineer, as the expert on this question of structural form, should probably be the one to educate the rest of the team, for starters. I think there are structural engineers who are very aware of this issue, and other ones that maybe don't care so much. And nowadays there's kind of a can-do attitude with the computer software that we use, that anything that you throw in the program, okay, we can make it work. It's just a matter of putting enough steel in it. So we do need to fight a bit against that and go back to our conceptual design, our hand calculation roots. But I think step one, the structural engineer needs to educate the rest of the team, because the architects and the owner don't necessarily know these things. They don't have They don't have the same background. What I found is when you do tell them, they say, oh, but yeah, that's obvious. Okay, well, now we know, and now we're not going to do that. And they like it because you're most of the time also saving cost and saving construction time, because building these transfer slabs is a huge undertaking. So if everybody can just be aware of this at the start, it really helps the process. And in part, that's why what I'm trying to do here is just point out this thing, which I hope you'll agree with me is kind of ridiculous when you look at it with the eyes of a physicist following the load path down.
Very good, thank you.
Thanks very much, David, for your very insightful presentation. My question is kind of related to Brian's, and that is, to what extent are we engaging practitioners, and more importantly, owner organizations, in understanding these things? And then the third group will be our students, because we train them appropriately to think in these terms. When they start to practice, then things are going to be different.
Yeah, great question. So let me just follow up with about engaging owners, and I think this is one of the things that we're trying to do within Globe, is to reach a different audience, to exit the echo chamber of our engineering professionals and get these messages to the people that essentially control the purse strings and can make these bigger decisions. But it's tough, because sometimes as engineers we're not experts in communication, so we need to talk to a different audience. We need to simplify our messaging and show things in a very digestible way. With regards to teaching and how we convey this to students, well, I'll say for my part, I try to bring this into my lectures and in my reinforced concrete and my master's course. I think conceptual design is a really important skill that sometimes gets lost in the sea of other things that we need to teach. And civil engineering has often been taught as, okay, this is how you design a beam, this is how you design a column, this is how you design a slab. But system level understanding, I think, is more important today than ever, because it's easy to put these things into a program and just say, okay, I'm going to extract my results, and this is my beam, this is my column, this is my slab. But somehow the whole is less than the sum of its parts, and if you just design a building like that, you'll find that you get other problems with differential settlement, and you get unexpected effects. So I think that we need to teach our students to have a better system-level understanding of structural behavior, specifically in the field of structural engineering. Thank you.
First of all, I'd like to congratulate you for this great lecture that you have given, and given so much of the insights here. I am from the University of Melbourne, and one of the pictures that you have shown here, the Melbourne School of Design, is where my office is. So I think I can see that building from the beginning when it was built, and today we are the beneficiaries of that particular building being the occupant. Now my question to you here is that you are talking about next 40 years, we are adding one New York City every month for that many years. So question here is that for who we are building these cities? Now to my view, I think the world has got two groups of people. One group of people lives in the cities, another group of people still today lives in the rural. So that means building those New York cities for next 40 years, we are simply encouraging or bringing those group of people, the 40% people in the globe who are in the rural areas at this moment, encouraging them to come and then living in those city settings. If those people are not coming to the cities, we do not have the demand at all, because our current 60% people already living in the urban settings, and they will also have to, of course, improve their living further, and we may have to build newer and better buildings, but the remaining 40% people, if they do not come to the cities, the demand is not there. So that is the reason why I started a program called Smart Villages program, trying to contain those 40% people in the rural settings, and they have got sufficient vernacular knowledge and ideas, and if we can somehow harness that, capitalize on that, those group of people, don't you think that will be better off living in the carbon neutral manner and compensating the remaining 60% people who are in the cities as of today and making that balance for the future? That is my question, and that is your views please.
Okay. Yeah, great point. I think maybe the statistic of building a new New York City every month is a bit misleading because it's just talking about floor space demand. It's not saying that we need to build all of this space as urban space. That's my understanding. But we still will have that population demand, whether the people are living in rural areas or urban areas. So I guess, and you would know better than me, but I guess the question is if in the rural areas there's a different typology that is more efficient than what we're currently doing. We would like to think that, okay, everybody's using biomaterials even in a rural setting, but that's not the case. There's a lot of bagged concrete, bagged cement that's being used to build this informal housing, and it's actually less efficient than multi-unit housing like what I show here. So I think it's an important question how we can optimize our demands for the different contexts as well. And I don't have an answer, but I'd be happy to talk more about your research and what you're thinking. And I'll also ask you the question: how do you enjoy having your office in that building?
So my colleagues are very much worried all the time, day in, day out. And they said if an earthquake hit Melbourne, the first people to die are those people who are living in that particular canyon.
Okay.
And they're saying all the time, the coffee shop and everywhere, that look, I'm sitting in my office, and something happens, I'm the first one to die.
So nice looking architecturally, but maybe functionally not even that great. Okay, thank you.
Yeah, thanks so much. It was a really nice presentation, and it was nice to see the donut economy coming into this context. My question is related to kind of, have we enough competency within the construction industry to manage these new thinking of donut economies and working within planetary boundaries? Do we need to kind of bring in more competency that can manage the biodiversity issues and looking at like ecosystems when we're thinking about building new structures or managing existing structures?
Yeah, great question. I think we tend to focus on certain wedges of that donut diagram more than others, but it has all of these multidisciplinary aspects, and having a team that involves people that are outside of the typical construction domain would definitely be a benefit as well. I think not all of these concerns are maybe equally pressing right now. So there is an immediate need to lower our carbon emissions, I'd say first and foremost before anything else, and to deal with the upfront carbon emissions today, because those are the ones that are going to have the most impact over time. So I think a balanced approach where, okay, let's tackle the big fish first, and then also integrate these other disciplines into the team and into our construction industry if possible.
I think we have time for one more question.
So David, just on that topic, just looking at the carbon tax aspect in changing mindsets or changing the narrative. So post COP21 and looking at nationally determined contributions, one of the main areas of focus has been that currently we're subsidizing, in essence, the use of cement and the CO2 emissions that come from the use of it for concrete, and that we should be really focusing on taxing it and changing the thought process when it comes to alternative materials. And we've seen positive developments in this space, especially in the use of fly ash, slag, in replacing almost all of the embodied carbon from cement in structures. So should we not, I mean, we're going to have to build these cities because the people are still coming, and that's unlikely to change very much in the next 40 years. So should that not be part of that discussion? Because, yeah, the transfer of beams is one aspect, but the physical structure still needs to be built, and whether it's steel, concrete, or timber, it's going to, you know, we need some kind of structural element to keep the building standing.
Yeah, so if I understood your question, it's about the materials we use and the fact that concrete is essentially, well, maybe artificially cheap or I don't know. Yeah, certainly there's a huge weight behind the concrete industry for sure. I'm not. I have no stake in the concrete industry. I'm not a cement shill. I think from a structural point of view, it's a good material, but I think that we can do better, and we need to incorporate these SCMs more. The problem with fly ash and slag is going to be supply. So we can't make all of our concrete for this you know, billions of cubic meters going forward with slag, which is why I personally like the LC3 solution. It has no problem with supply. It's something that we can do everywhere with little capital investment to upgrading existing cement plants. But like I said, by all means, I'm 100% for using the right material in the right context, and if somebody can do an analysis and decide that you know, concrete should be taxed higher, well, then maybe that's the way to go. Not a super satisfactory answer, but thank you.
Okay, thank you very much, David. Ryan would like to come up and say a few things.
So David, on behalf of CIB and Purdue University, and we really appreciate you presenting this information. Great talk today, so thank you very much. And we wish you the best with Globe.
Thank you.
Thank you very much. All right. Thank you. Great job. Great job. So we had a great talk there from David. We've got a number of great sessions going on here, just starting up around 10:30. I do want to note something kind of unique in the schedule. The National Academy of Constructors is running a safety symposium, and that is in Stewart 218. So Stewart 218, that's where our industry forum was yesterday. Something you may want to stop in there and check that out too. That is actually ongoing now, so if you want to jump in on that before some of the sessions get started, I encourage you to do so. So enjoy your day. Thank you.